Vsauce, Michael here. Do you have a best friend who is there for you 24/7, 365? Sorry, that's not really good enough. If your friend truly had your back, they would be there for you 24.0000067 365.2421891. Also, George Washington was born on February 22nd, 1732. At least, that's what we're told. However, his family Bible says he was born on February 11th, 1731/2. So, which is it, Mr. I cannot tell a lie? Oh, and don't even ask about 1752. In Russia, 1752 looked pretty normal, but check out what the British Empire was up to that year. Nothing really out of the ordinary, except Ember. The second was followed by the 14th. Were 11 days just deleted? Where'd they go? What happened then? It is time to question time and how the Earth moves. Reconciling both of these things has led to some pretty strange things. We all love time-lapse videos of the stars moving across the sky. But really, we are the ones who are moving, tumbling through the universe on a giant, wet rock vehicle called Earth with a windshield called the sky. As viewed from above the North Pole, we spin counterclockwise. West chases east. I always remember this by thinking of the US as a weird, mane-headed animal with Texas and Florida legs running forward. But we don't just spin. We also revolve around the sun on a plane tilted 23.4 degrees relative to our spin. It's kind of nauseating at this scale. But from this perspective, you can see that the sun rising and setting is just the Earth pointing you towards and then away from the sun. This motion causes your sunrise, your noon, the moment when the sun is highest in your sky, before your sunset. To more closely investigate this movement, let's talk about meridians. You are on one at this very moment. Your meridian is just a line from where you are right now, straight towards the north and south poles. It's a line of longitude, as opposed to the horizontal lines that lay flat when north or south is up that we call flatitude, or actually latitude. The sun is highest in the sky to you, your noon, when your meridian is pointed right at the sun. A cool thing happens at this moment. All shadows around you point directly towards one of Earth's poles, unless you're on the subsolar point. The subsolar point is the point on Earth's surface directly below the sun. It's always somewhere. You can check its current location online, links as always in the description. On the subsolar point, shadows fall straight down so they can easily disappear. Twice a year, the subsolar point crosses over Hawaii, the only place in the US where it hits land. And when it does, it is called Lahaina Noon, meaning cruel sun. Straight vertical objects look unnatural during this brief time, like they don't belong, as if they were photoshopped in without regard for reality. In Honolulu, a sculpture by Isamu Noguchi called Skygate casts a twisted shadow all day, every day, except during Lahaina Noon, when its shadow is a perfect circle. You may not live in a place where the sun ever appears directly overhead, but once every Earth rotation, the subsolar point falls somewhere on your meridian, making it noon for you. The technical name for this noon for you is local apparent solar noon. The clock on your wrist and the clock on your phone don't tell you your local apparent solar time, because long ago we realized that if every meridian had its own time, a person just a few kilometers away seeing different shadows than you did, would disagree with you on what time it was. So towns adopted their own time. Now later on, this trick was standardized and time zones as we know them today came about. But that's not all we didn't like about shadow-based sundial time. To explore deeper, we have to begin by asking, what's a day? I mean, obviously it's just the time it takes the Earth to turn around once, right? But according to what? Everything else in space is moving in some way too. The universe doesn't include a convenient sheet of graph paper at absolute rest we can trace paths on. The best we can do on that front is to look at very, very far, far, far away stars. So far away, like distant features of the landscape out the window of a moving car, they barely move as Earth does. Now, to them, a meridian on Earth completes a trip around about once every 23.9 hours. This is called a sidereal day. Sidereal means pertaining to the stars. Even though the sidereal day seems pretty clear, it's not what our calendars and clocks are based on, because there's a nearer star whose position relative to us has a bigger effect on our lives: the sun. Looking down on the North Pole at Earth's counterclockwise spin, the Earth also moves counterclockwise around the sun. After a sidereal day, the Earth has moved a bit along its orbit, so some more rotation is required for the same meridian to point back towards the sun again. This longer definition of one rotation is what the modern calendar and clock is based on. It is called the solar day. But here's the thing. Exactly how long the Earth has to rotate to complete a solar day changes day to day. Our clocks are just based on the average amount of time this takes, so throughout the year, they fall ahead and behind the sun. This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't. In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks, called equation clocks, were made that would do this for you, but eventually, we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing up. It was like the first time you realize you're stronger than your parents. We realized our timepieces were more regular and turned our backs on the timepieces nature had. But what causes this disagreement in the first place? As it turns out, the answer revolves around revolving, the way the Earth revolves around the sun. If the equator faced the sun all the time and the Earth always orbited at the same speed, the subsolar point would just stay right there on the equator throughout the year, and the amount of extra time spent rotating the Earth needed to do to finish a solar day would always be the same. But those two things aren't the case. First of all, the Earth's orbit is slightly elliptical, so its speed varies throughout the year. When it's moving around the sun faster around the beginning of January, the amount of extra turning time needed to complete the solar day is longer than when it's further away from the sun and moving more slowly. There's more. Because the Earth is tilted, the subsolar point is dragged throughout the year in a circle around Earth that's not the equator, so it changes direction, moving northeast, then leveling out and going southeast, before leveling out and going northeast again. During times of the year when the subsolar point is being dragged by Earth's orbit mostly east, it gains against Earth's spin faster, more time is required for the day to finish. Now, by coincidence, we are alive at a time when both of these phenomena lengthen and shorten days at roughly the same time. So they add up, making September 18th almost a minute shorter than the longest day of the year, December 22nd. For Northern Hemispherians, December has the shortest periods of daylight, but the whole solar day, from sunrise to sunrise, is for everyone on Earth the longest of the year on December 22nd. People in the north just spend most of it in darkness. Earth's tilt doesn't just affect how long a day is, it also affects how long a year is. This is because the Earth's tilt is what causes the seasons. For the half of the Earth tilted towards the sun, the same amount of solar radiation is spread across less space than it is on the other half, so there's more heat energy laid down per area. This causes what we call summer and winter for the other half. The amount of time from one of these seasonal orientations of the Earth to its occurrence again is called a solar year, or a tropical year. It's a very useful way to define a year because it contains every single season exactly, since it's based on the very orientations that cause them. But the problem is this: the number of solar days that occur in a solar year is not a whole number. It's almost 365. But after that many solar days, about a quarter of a day more happens before the solar year starts again. This makes designing a calendar more like designing a calendar. If your calendar only ever has 365 days in a year, over time, those dates will drift from the seasonal positions they used to occur during. Unless, this extra quarter of a turn adds up to a full day after 4 years. See, March 1st is coming a day too soon now, so if we just delay March by adding an extra day at the end of February every 4 years, a leap day, we're back on track. Leap days do not add days to your life. You're still going to live the same number of them. They just change what we call them. But really, who cares about being 1 day earlier every 4 years? I mean, 1 day isn't much, you'd hardly notice it. But over time, well, if America's founders had declared not only independence from Britain, but also from leap days, and abolished them from happening, today, 240 years later, their calendar would be a full 2 months ahead of Earth's position, putting America's coldest winter days in April and its hottest summer days in October. Adding a day every 4 years is what the famous Julian calendar does. Introduced in 46 BC by Julius Caesar, it was the de facto standardized Western calendar for a very long time, more than a millennium. But it's not perfect. Look closely. Leap days actually move the calendar just slightly too far each time, because I lied. 365¼ solar days don't occur within one solar year. The real number is slightly less and fluctuates year to year based on long-term changes to Earth and the Sun's movements, which means adding 1 day every 4 years is just a teensy-weensy too many. By 1582, Julian calendar dates were 10 days behind the seasons compared to where they used to be. Now, that's not bad, 10 days in more than a millennium and a half. But the Catholic Church cared, because they wanted Easter to occur exactly when it used to centuries ago. Astronomers at the time realized that if leap days pushed the calendar too far behind the seasons, we would just need to celebrate fewer of them to fix the problem. Specifically, we would need 3 fewer leap days every 4 centuries. The rule they wrote to achieve this stated that every 4 years would continue to be a leap year, except if it was divisible by 100, unless it was also evenly divisible by 400. This removes 3 every 400 years. On October 4th, Pope Gregory XIII introduced this new calendar. It took his name, the Gregorian calendar. He also undid the drift that had occurred since the early days of the Julian and declared on October 4th that tomorrow would be October 15th. October 5th to the 14th never happened in 1582 in countries that listened to the Pope. It took the rest of the world centuries to hop on board. England and its colonies, like the soon-to-be United States of America, adopted the Gregorian in September of 1752, by which point their Julian dates were off from the seasons by 11 days, hence the disappearing of the 3rd through 13th. When adopted, the first of the year was also moved from March to January 1st. This explains why George Washington's birthday has two answers. Although more closely hitched to the seasons than the Julian, the Gregorian calendar still isn't perfect. Its difference causes dates to become one day off from the seasons every 3,216 years. Other calendars have been proposed, like the one Stand Up Maths calculated that drifts off even more slowly. His video is a great watch, by the way. But enough of all of this. Let's sit back and enjoy Earth's movement without trying to divide it up and name it. As a caveat, keep in mind that Earth's oceans and liquid insides and other celestial bodies are always pulling and tugging and sloshing around, minutely changing Earth's movements. Their effect is measurable, but difficult to notice at big scales and also don't look like much in the short term. Short, like the length of a human life. Looking from above the North Pole, the equator spins counterclockwise at about 1670 kilometers per hour. Relative to the sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path tilted 23.4 degrees to its spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way, on a plane tilted about 60 degrees, approximately like the windshield of a car. Looking from above Earth's North Pole, our entire solar system races clockwise around the galactic center at about 792,000 kilometers per hour. Our whole galaxy is also moving through the universe. We know this because when the universe was very young, it was so hot, electrons and protons jumped around, and photons of light scattered constantly. They couldn't travel very far before scattering again, so the universe was opaque. But then, around 380,000 years after the Big Bang, the universe cooled just enough for electrons and protons to form hydrogen. Suddenly, abruptly, photons decoupled from this obstacle course and could travel relatively unencumbered. The universe became transparent to light. And since that moment, those early photons have been propagating through space. Every day, ancient photons that last scattered off this opaque fog at the moment of decoupling, a light day further from where Earth currently is, reach us. They are part of the cosmic microwave background radiation. It is visible in every direction. Microwave because although they used to be more energetic, the universe's expansion has redshifted them. Now, some parts of this radiation are more redshifted than others because of our own movement through the universe. Controlling for the movements we've already talked about, relative to this infinite, cooling baby picture of the universe, the first and oldest detectable light, we are headed, riding along in the Milky Way, in the direction that the constellations of Leo and Virgo are to us, at a speed of 2.1 million kilometers per hour, towards a thing we don't fully understand yet, simply called the Great Attractor. This is how you, on Earth's surface, are moving through the universe aboard Spaceship Earth. Okay, now stop. This is roughly 100 years of Earth's movement through space. This path we've traced, from where we began here, is the path you will take through the universe in your lifetime. You didn't buy a ticket for this ride. Your parents signed you up without asking. But nonetheless, it is quite literally the ride of your life. And as always, thanks for watching. It is now time for a major Vsauce announcement. You know how for the last couple of years we've released a holiday box? Well, introducing the Curiosity Box by Vsauce. We created this thing as a quarterly box. This comes to you 4 times a year, and it comes packed with amazing, exclusive Vsauce merchandise and incredible geeky toys picked by myself, Kevin, and Jake. Plus, as always, a portion of the proceeds from this box goes to funding Alzheimer's research. You can get your own by subscribing at thecuriositybox.com. I'm incredibly proud of this. Go check it out. And as always, thanks for watching.